In 1989, the most provocative Cyrix product was not a processor at all. Open a powerful 386 class PC, and the most important chip on the motherboard was still likely to carry Intel's name. The 80386 controlled the machine, ran the operating system, and executed the software that had made the new generation of PCs desirable. Nearby, however, many systems provided another socket for a far more specialized device. Engineers, scientists, designers, and other users working with demanding numerical software could install an 80387 math coprocessor there and move a large amount of floating point work out of software and into dedicated hardware. Intel had designed the processor architecture, and its own 80387 was the obvious companion. Then, a small company in Richardson, Texas, appeared with another answer. Cyrix had been founded only recently and had never released a CPU. Its first commercial product was instead a numerical coprocessor called FasMath, designed to work in the same environment as Intel's 387 class hardware. From the software's point of view, the compatibility was the essential requirement. Programs written to use an 80387 expected a particular instruction set, numerical formats, processor state, and behavior. A replacement that failed those expectations would have little value regardless of how clever its internal circuitry might be. FasMath was intended to enter that established environment without asking software developers to rewrite their applications around a new mathematical architecture. What made the chip interesting was what happened after it entered the socket. Contemporary testing found that Cyrix could outperform Intel's own 80387 in important floating point work, while technical advertising of the period emphasized especially strong results in operations that could keep a numerical processor busy for many cycles. A 1991 comparison of 387 class coprocessors placed the Cyrix 83D87 ahead of both the original and revised Intel 80387DX in its whetstone test, although the size of the advantage changed greatly with the workload being measured. That distinction matters. FasMath did not make an entire 386 PC universally faster, and ordinary applications that performed little floating point mathematics might barely notice its presence. Cyrix had found something more specific, and strategically more interesting. In the small part of the machine where numerical performance could be compared directly, a company with no CPU product of its own had entered an Intel-defined environment and shown that Intel's implementation was not automatically the fastest one available. The processor socket still belonged to Intel. Cyrix had not yet attempted to replace it. For the moment, the startup was proving itself through the quieter socket sitting beside it. Before understanding how that challenge was possible, however, there is a more basic question to answer. Why did a machine as advanced as the 386 need a second processor just to handle mathematics? The 80386 was one of the most capable personal computer processors of its generation, yet an important category of mathematics still sat outside the CPU itself. Intel had given the chip a full 32-bit architecture, greatly expanded memory addressing, protected operating modes, and enough general-purpose performance to open the PC to increasingly sophisticated software. Floating point calculation was handled differently. A 386 system could perform that work without another processor, but operations intended for Intel's numerical architecture then had to be handled through software emulation, which Intel acknowledged required substantially more execution time than dedicated coprocessor hardware. For many users, that difference hardly justified another expensive chip. Word processing, communications, and much ordinary business software spent most of their time doing work for which an FPU offered little advantage. Technical applications could present the opposite situation. CAD geometry, scientific analysis, engineering models, and other numerical programs repeatedly manipulated values that could contain fractions, enormous ranges, or calculations far more demanding than ordinary integer arithmetic. When enough of an application's workload consisted of that kind of mathematics, waiting for software routines to reproduce floating point operations could become a meaningful bottleneck. The 80387 existed to remove it. Intel designed the chip as a numerical extension to the 80386, adding hardware for high-precision integer and floating point calculations, comparisons, square roots, transcendental functions, and the numerical formats expected by the x87 software environment. The architecture also followed the IEEE floating point standard that had become increasingly important for predictable numerical computation. From the programmer's point of view, the relationship between the two processors was unusually seamless. Coprocessor instructions appeared in the same instruction stream as ordinary CPU operations. When the 386 encountered one, its coprocessor interface coordinated the operation with the 387. Intel designed the two devices so that numerical work could proceed concurrently with CPU execution when dependencies allowed it. When a result was required before execution could continue, Synchronization mechanisms, such as the wait instruction, brought them back together. A suitably equipped 386 PC therefore contained two processors performing different kinds of work. The 80386 remained responsible for the general execution of the machine, while the 80387 specialized in numerical operations that could otherwise consume far more time in software. The important detail for the Cyrix story was physical as much as architectural. That floating point engine was not yet integrated into the 386 processor die. It remained an optional component occupying a separate position in the system. Intel had defined how numerical software expected that environment to behave, but a computer manufacturer or owner did not necessarily have to place an Intel-manufactured coprocessor in the socket. A competing semiconductor company could concentrate on that one highly specialized problem rather than attempting to replace the entire 80386. If it could preserve the behavior existing software expected while finding a faster way to execute the mathematics, it could challenge Intel without yet possessing a CPU of its own. For Jerry Rogers and Tom Brightman, that narrow opening would become Cyrix's first battlefield. Jerry Rogers and Tom Brightman entered the x86 market from a very different position than Intel. They were experienced semiconductor engineers, but they were not arriving with a fabrication network, an established processor family, or customer base already committed to their architecture. Rogers had spent 16 years at Texas Instruments and had managed its microprocessor division, while Brightman had worked at TI before moving through companies including Atari and Commodore. When they helped establish Cyrix in Richardson, Texas in the late 1980s, the company began not with a general-purpose CPU, but with these specialized numerical processors designed to accompany 286 and 386 class systems. That choice placed Cyrix inside an existing market without requiring customers to adopt a new kind of computer. Intel had already supplied the processors. PC manufacturers had already built machines around them, and engineering software already knew how to use the x87 numerical environment. Cyrix could enter through one component of that established system and let the existing software provide the test. The component was small compared with the CPU, but the engineering problem was not. A math coprocessor had to perform demanding arithmetic accurately, respond the way existing programs expected, and cooperate closely enough with the host processor that the substitution remained invisible to software. Customers using CAD or scientific applications were unlikely to tolerate a chip that was merely almost compatible, particularly when a wrong numerical result might be more dangerous than an obvious crash. At the same time, the problem had a useful boundary. Cyrix did not yet have to take responsibility for every integer instruction, operating system mechanism, memory management function, and control path inside a complete x86 CPU. Its engineers could concentrate on numerical execution and the interface through which the processor communicated with it. That gave the young company somewhere practical to demonstrate what its design talent was worth. Intel's 80387 already established the behavior customers expected, so Cyrix did not need to persuade software developers to support an entirely new mathematical system. If its chip could enter the same environment, run the applications already written for it, and complete important calculations more quickly, the improvement would become visible without requiring the rest of the PC industry to change around Cyrix. The significance went beyond the size of the market for coprocessors. A successful product would demonstrate that an Intel-compatible component could be designed independently and still compete on more than price. For engineers who would later attempt complete x86 processors, that was valuable experience to acquire first. Cyrix could learn where compatibility mattered most, how real applications exposed differences that specifications alone might miss, and how an independently designed execution engine behaved once it left simulation and entered customers' machines. Rogers and Brightman had therefore entered Intel's ecosystem through a secondary socket, but there was nothing secondary about the technical standard they would have to meet. The next challenge was to produce the same outward mathematical behavior software expected, while building a very different machine underneath it. For Cyrix, building a faster arithmetic engine was only half of the problem. FasMath had to enter a 386 system whose software had been written with Intel's numerical architecture in mind and behave closely enough that the substitution required no new programming model. An application issuing an x87 instruction expected more than a calculation eventually appearing somewhere in memory. It depended on familiar data formats, the 8-register numerical stack, status and control information, exception behavior, save processor state, and the communication between the main CPU and its coprocessor. Cyrix's own documentation presented the 83D87 as a hardware and software compatible replacement for the 80387, with support for IEE floating point arithmetic and the established XDD7 programming environment. Those expectations placed strict boundaries around what software was allowed to see. They did not, however, tell Cyrix exactly how the calculations had to be performed inside the silicon. That distinction created the room in which the company could compete. The instruction asking for a division still had to behave like the instruction an application expected. The state left behind after the operation still had to make sense to existing software, but the internal circuitry used to reach that point did not have to reproduce Intel's 80387 transistor for transistor. Cyrix could organize its arithmetic hardware and control logic around its own design decisions, then expose the familiar behavior at the boundary where the rest of the computer interacted with it. Later court findings offer unusually concrete evidence of how substantial that independent engineering effort was. The FasMath devices contained more than 200,000 transistors, and the court found that Cyrix carried out the initial circuit design through manual engineering and computer simulation before manufacturing-specific information was added for fabrication. That mattered because floating-point operations do not all cost the same amount of work. A simple addition and a transcendental calculation, such as a logarithm place, very different demands on the hardware performing them. An independent design team therefore had opportunities to reorganize the internal execution of expensive operations without asking programmers to learn a new instruction set. If the external behavior remained compatible, an application written years earlier could benefit from those internal decisions simply because a different coprocessor had been placed in the socket. That made compatibility something more interesting than imitation. Cyrix was constrained by the interface Intel had established, but it was not forced to treat Intel's implementation as the only possible implementation. Of course, freedom inside the chip created its own danger. A numerical processor that was dramatically faster but mishandled an exception, restored its state incorrectly, or produced results outside what real applications tolerated would fail precisely where Cyrix needed trust most. FasMath therefore had to prove two things simultaneously: that software could treat it like a credible member of the 387 environment, and that Cyrix's different internal design was worth choosing. Once physical chips began running real numerical workloads, the first requirement would determine whether FasMath was usable. The second would determine whether anyone noticed Cyrix at all. When FasMath finally reached real 386 systems, Cyrix could test the proposition that had justified the entire project. Compatibility had earned the chip a place in the same numerical environment as Intel's 80387. Now the question was whether Cyrix's different internal design actually bought anything once the calculations began. A 1991 Computercraft comparison gave one of the clearest answers. The magazine tested Intel's original 80387DX, a revised Intel version, IIT's competing 3C87, and Cyrix's 83D87 in a 20 MHz 386DX system. Intel's newer coprocessor was already much faster than its first implementation, so Cyrix was not simply being compared with an obsolete design. Even so, FasMath finished ahead. In one benchmark, it delivered 1,427.2 K whetstones per second against 1,197.7 for the revised Intel part. In the second test, the result was 812 against 660. That put the Cyrix device roughly 19 to 23% ahead under those particular conditions. Those numbers did not mean replacing an Intel coprocessor with FasMath made an entire PC 20% faster. The gain appeared only when software actually spent enough time performing floating-point work for the coprocessor to matter. A spreadsheet dominated by ordinary program logic might show little difference, while an engineering calculation repeatedly exercising the FPU could expose a much larger one. Even within numerical software, the instruction mix mattered because some operations were dramatically more expensive than others. That was where Cyrix's architectural choices became especially visible. Contemporary advertising for FasMath emphasized long-running operations such as division, square root, logarithms, and transcendental functions, with Microwave claiming that some of them executed 2 to 4 times faster than the equivalent operations on an 80387. Those figures were marketing claims rather than a promise about complete applications. But they help explain why the overall benchmark advantage could conceal much larger differences inside individual instructions. For Cyrix, the important achievement was therefore not a single headline percentage. The company had designed a 387 compatible device independently, placed it beside an Intel 386, and demonstrated through third-party testing that Intel's own numerical processor was not automatically the fastest implementation of the environment Intel had created. That was an extraordinary result for a company that still had no general-purpose CPU on the market. FasMath was beginning to give Cyrix something startups rarely acquire so quickly in the processor business: technical credibility. A buyer could now choose the Cyrix name for more than price or novelty. In workloads that genuinely depended on floating-point computation, there was measurable performance behind it, but numerical hardware imposed a harsher standard than speed alone. An engineering program that finished sooner was worthless if the answer was wrong, and a coprocessor that won a benchmark but failed an application could destroy the trust Cyrix was trying to build. FasMath had demonstrated that Cyrix could make the mathematics fast. The next challenge was proving that existing software could rely on it. FasMath had shown that Cyrix could make floating point calculations fast. The harder question was whether anyone doing serious numerical work could afford to trust it. A math coprocessor lived in an unusual part of the computer because an error did not always announce itself by crashing the program. An engineering calculation might continue running even if something subtle had gone wrong in rounding, exception handling, or the numerical state carried from one operation to the next. For users depending on CAD, scientific analysis, or financial models, a fast answer was valuable only if it remained the answer the software expected. That placed a much heavier burden on compatibility than simply fitting into the same socket. Existing applications had been written around Intel's x87 environment. They expected familiar data formats, control and status behavior, saved numerical state, and predictable responses when a calculation reached an exceptional condition. Cyrix therefore had to make FasMath disappear from the user's point of view. The hardware could be different internally, but the software above it should have as little reason as possible to care which company's silicon was performing the mathematics. Cyrix's own installation material reflects how practical that goal had become. The 83D87 was presented as a replacement for an Intel 80387 compatible coprocessor in existing 386 systems, with users instructed to place it in the same coprocessor socket and configure the machine as required by the motherboard. The manual also made an important point about performance. Applications that did not use floating point calculations would see no benefit at all, while software performing more numerical work would make the advantage increasingly visible. By 1991, Cyrix was advertising FasMath directly around familiar software rather than around synthetic arithmetic alone. Its marketing referenced Lotus 1-2-3 and emphasized compatibility testing performed by Lotus Development, showing how strongly Cyrix wanted buyers to associate the chip with software they already trusted. Those claims came from Cyrix's own advertising and were therefore promotional rather than an independent guarantee of every possible application. But they reveal the commercial problem clearly. Winning benchmark charts was not enough. FasMath had to feel ordinary once installed. The product was also spreading beyond the original 386DX version. By the time Cyrix and Intel were in federal court in 1992, the record identified a FasMath family containing the CX83DA7, CX83S87, and CX82S87, alongside the company's AutoMath devices. The 83D87 addressed 386DX class systems. The 83S87 served the 308.6SX environment, and the 82S87 extended Cyrix's numerical technology into 286 class machines. That expansion says more than another benchmark could. Cyrix had moved beyond proving that one experimental design could outrun Intel under selected conditions. It was building a business around the assumption that computer owners and system manufacturers would accept independent, numerical hardware inside machines whose CPUs still came from Intel. The substitution had to become routine enough that the user could think about the application instead of the coprocessor. By then, Cyrix had demonstrated the two qualities its first entrance into x86 required. FasMath could deliver genuine performance, and it could participate credibly in the software environment that gave that performance value. The next challenge would come from outside the arithmetic engine itself. Cyrix could design the silicon, but it did not own the fabrication plants needed to manufacture it. That dependence on outside semiconductor partners would soon pull the company into a confrontation with Intel in which patents and licensing mattered as much as transistor design. Once FasMath had become a credible product, Cyrix encountered a problem that had nothing to do with how quickly its arithmetic engine could divide two numbers. The company could design advanced semiconductor circuits, but it did not own the factories required to turn those designs into physical chips. FasMath therefore depended on outside manufacturing, and one of Cyrix's most important partners was SGS Thomson Microelectronics. Federal court findings from 1992 provide an unusually detailed picture of that relationship. Cyrix performed the initial FasMath circuit design and developed it through engineering and computer simulation. SGS Thomson then supplied manufacturing-specific rules and process information, completed the work needed to translate that design into its fabrication process, created the masks, manufactured the wafers, tested the dies, and transferred finished devices back to Cyrix. For a small semiconductor company, the arrangement was enormously powerful. Cyrix could concentrate its resources on architecture without first building an expensive fabrication plant. But outsourcing production also connected the company to a legal structure that most buyers would never see. In 1977, Intel and Mostek had signed a patent cross-license allowing each company broad rights to manufacture and sell products covered by the other's patents. Mostek later passed through corporate changes and SGS Thomson eventually acquired substantially all of its relevant assets. That old agreement became crucial when Intel asserted patent rights against Cyrix's FasMath coprocessors. The legal question was no longer simply whether Cyrix had designed its circuitry independently. If SGS Thomson had inherited Mostek's Intel license, then chips manufactured under that license could carry protection that Cyrix itself did not possess directly. In 1992, the federal court concluded that ST had validly inherited the Intel Mostek agreement. Intel had also stipulated that if ST owned that license, the FasMath devices ST manufactured and transferred to Cyrix qualified as licensed products. The court then applied patent exhaustion. Once an authorized licensee had made and disposed of those particular devices within the scope of its license, Intel could not use the patent at issue to control Cyrix's later use or resale of them. The decision suddenly made the identity of the factory part of Cyrix's competitive strategy. Microprocessor Report described the ruling as having potentially broad implications for independent chip designers because a suitable foundry license could provide protection even when another company had designed and marketed the processor. Yet the same report showed the limitation. Some early FasMath wafers had been fabricated by TSMC, which did not possess the same Intel agreement, so those devices were not automatically sheltered by the SGS Thomson ruling. Cyrix had discovered something important about competing inside the x86 market. Good architecture could create the product, but architecture alone did not determine whether that product could reach customers safely. Manufacturing relationships, old cross-licenses, and intellectual property claims could become part of the competitive landscape surrounding the silicon. The fabless model gave Cyrix access to advanced manufacturing without owning a fab of its own. It also meant that the legal position of the company manufacturing the chip could matter almost as much as the process technology being used. FasMath had now survived tests of performance, compatibility, and a serious patent challenge. By 1992, Cyrix was ready to apply what it had learned to a much larger target. The company that had entered the x86 world through the socket beside Intel's processor was preparing to put its own name on the processor socket itself. For the first years of Cyrix's existence, its name appeared beside the main processor rather than on it. In 1992, that changed. The company that had earned credibility through FasMath was ready to move from designing the numerical engine beside an Intel CPU to designing the CPU itself. Its first step was the CX486LC, announced in the spring of that year. Despite the 486 in the name, the chip was not a pin-compatible substitute for Intel's 486DX. Cyrix designed it around the electrical environment of the 386SX, giving system manufacturers a processor with a small on-chip cache and a more advanced internal core, while preserving a bus architecture they already knew how to build around. Contemporary reporting presented the SLC as a way to deliver some of the appeal associated with newer 486 class machines at a price closer to Intel's lower-cost 386 products. Cyrix followed with the CX486DLC only a few months later. Microprocessor Report identified it as the company's second microprocessor and described it as a 32-bit bus version of the SLC, pin-compatible with the 386DX rather than Intel's 486DX. That distinction reveals how Cyrix entered the CPU market. It was not attempting to reproduce Intel's newest processor package exactly and ask motherboard manufacturers to substitute one chip for another. It was using familiar 386 class system environments as a way to introduce its own processor. Core into machines, manufacturers could adapt without redesigning everything around Intel's 486 bus. The strategy carried several lessons from FasMath without making the two designs the same thing. A floating-point coprocessor and a complete x86 CPU presented very different engineering problems, and FasMath did not simply evolve into the SLC or DLC. What the earlier products had given Cyrix was experience implementing Intel-compatible behavior independently, discovering where real software exposed compatibility problems, working with outside fabrication partners, and convincing customers that a chip carrying the Cyrix name could belong inside an x86 system. The CPU market demanded all of that at a much larger scale. A complete processor now had to execute the general x86 instruction stream, manage control flow and exceptions, interact constantly with memory and the system bus, and survive the enormous variety of software accumulated around DOS and Windows PCs. Cyrix continued relying on outside manufacturing as it made that transition. Texas Instruments joined SGS Thomson as a foundry partner and also obtained marketing rights to Cyrix processors, allowing the design company to expand production without owning a fabrication plant itself. The company even preserved a direct link to its original business, by offering the 486 DLC with a separate CX87 DLC math coprocessor. But by then, the wider processor market was already moving in another direction. Intel's 486DX, introduced in 1989, had combined a complete floating point unit with the CPU on the same processor die, while the lower-cost 486SX removed that working FPU for buyers who did not need it. Cyrix had finally reached the processor socket, but it was doing so after the industry had already begun collapsing the two-chip CPU and coprocessor arrangement that had created its first opportunity. FasMath had helped Cyrix become a processor company. The architecture of newer processors was now beginning to erase the separate market that had made FasMath possible in the first place. By the time Cyrix placed its own name on an x86 CPU in 1992, the market that had given the company its first opportunity was already beginning to disappear. FasMath had been possible because floating point hardware remained physically separate from the main processor in 286 and 386 class systems. A customer who needed serious numerical performance could add the coprocessor. Someone who did not could leave that part of the machine out. That separation had given Cyrix a remarkably useful entrance into Intel's architecture. The company could attack one demanding execution problem without first having to design the complete CPU around it. Intel's 486DX changed the direction of that architecture. Introduced in April 1989, the new processor combined general-purpose execution, an on-chip cache, and floating point capability within the processor itself. In a high-end 486DX machine, the numerical engine was no longer a separate choice sitting beside the CPU. It had become part of what the processor was. The transition did not eliminate standalone coprocessors overnight. The enormous installed base of 286 and 386 systems still created demand for numerical upgrades, and lower-cost processor designs could continue separating those functions. Cyrix's own first CPUs demonstrated that clearly. The CX486SLC and CX486DLC, introduced in 1992 and designed as enhanced processors, compatible with 386SX and 386DX class system environments, did not contain the kind of integrated floating point unit found in Intel's 486DX. They could still be paired with separate Cyrix numerical hardware. Yet the long-term direction was becoming difficult to ignore. For new high-performance processors, floating point execution was moving from an optional accessory toward a function expected inside the CPU itself. That created a peculiar moment for Cyrix. The company had built its reputation by showing that Intel's numerical processor could be replaced. Just as that success gave Cyrix enough technical credibility to enter the CPU business, the architecture was removing the independent socket that had made such a focused challenge possible. The change did not erase the value of what Cyrix had learned. Designing FasMath had forced its engineers to understand x87 behavior, numerical precision, software compatibility, and the performance consequences of internal arithmetic design. Those skills remained relevant even when the FPU no longer needed its own package. What changed was where they had to be applied. A company hoping to compete in future x86 processors would increasingly have to treat integer execution and floating point performance as parts of the same processor design problem. FasMath therefore belonged to a technological window that was beginning to close. It had given Cyrix a business, a reputation, and a route into the x86 world precisely because the processor had once been incomplete without an optional numerical companion. By the time Cyrix became a CPU company, that distinction was fading. The secondary socket that had allowed Cyrix to challenge Intel first was becoming part of the processor socket Cyrix now wanted to challenge directly. By the time Cyrix released its first complete x86 processor in 1992, FasMath had already answered the question that mattered most for the company's future. Could a small independent design team enter an environment defined by Intel, preserve the compatibility that made that environment valuable, and still build a better implementation of part of it? The 83D87 had shown that the answer could be yes. Cyrix had not asked software developers to adopt a new numerical architecture. It placed its chip into systems already built around the 386, and executed the x87 operations existing programs expected. What changed was the hardware hidden underneath those expectations. In a 1991 comparison, the FasMath 83D87 finished roughly 19 to 23% ahead of Intel's revised 80387DX in the two benchmark suites used by Computercraft. The reviewer was careful to note that real application gains depended heavily on how much floating point work a program performed and which instructions it used, but the broader result remained difficult to dismiss. Under comparable conditions, an independently designed Cyrix coprocessor could outperform Intel's own part. That achievement was narrower than saying Cyrix had beaten Intel. Intel still supplied the processor at the center of the machine, controlled an enormous manufacturing organization, and remained the company defining the direction of the x86 market. FasMath accelerated only the numerical work for which it had been designed, and many ordinary applications would gain little from replacing one coprocessor with another. Its historical importance came from what the comparison proved, rather than from the percentage itself. The visible interface of an architecture and the internal implementation behind it were not the same thing. Cyrix could respect the former without reproducing the latter. That lesson had shaped the company before it ever sold a CPU. Developing FasMath forced its engineers to understand which details real software actually depended upon, where numerical compatibility could fail, and how different internal execution choices could alter performance without requiring applications to change. Manufacturing the product through outside semiconductor partners also showed that a design company did not need Intel's fabrication scale to place sophisticated x86 compatible silicon into the market, even though the later patent dispute demonstrated how complicated that independence could become. Federal court findings would confirm that Cyrix performed the initial FasMath design while SGS Thomson handled substantial process-specific work and physical fabrication. By 1992, Cyrix was ready to apply that experience to the primary processor socket. Contemporary reporting described the company's 1989 math coprocessor as its first product and its 1992 processor as the move into full-fledged microprocessors. The separate FPU market that had created Cyrix's opening would eventually fade as floating-point execution moved onto the CPU die, but the argument proven by FasMath survived the socket that had made it possible. Cyrix had entered Intel's ecosystem through one specialized piece of hardware and discovered that compatibility could provide a foundation for competition rather than a command to imitate. Before Cyrix challenged Intel for the processor socket, FasMath had already proved its central argument. Compatibility with Intel did not require being slower than Intel.